4.6 is applications and models of exponential growth and decay. We'll start off with a exponential growth or decay function. Let y sub o be the amount or number present at t equals 0. Then under certain conditions, the amount y present at any time t is modeled by y equals y sub o e to the kt, where k is a constant. Now this may look familiar to you because this is the same formula as continuously compounded interest. P of t equals P sub o e to the RT, or the PERT formula, and you can remember that because there is a shampoo called PERT. So a lot of people refer to this as the PERT formula. So you don't really need to memorize another formula, just use PERT. The formula is going to cause an increase or growth if the rate here is, that's your relative growth rate, if it's a positive. And if it's a negative, then we're going to have an exponential decay. So it's one formula for both of those, and it's a formula that you really already know. So we have a couple of concepts we want to talk about when we talk about growth and decay exponentially. The growth model functions, we have something called doubling time. This is the amount of time it takes for a quantity that grows exponentially to become twice its initial amount. So let's say we started out with 10 bacteria and we were growing like this. And so we want to know from here to here, what is the time? So it's that horizontal amount of time, whatever this is on the scale on this horizontal axis, that is the doubling time that it takes for the initial 10 to become an amount of 20. Decay function models will talk about half-life. Half-life is when we have that continually decreasing model. It's the amount of time that it takes for a quantity that decays exponentially to become half of its initial amount. So let's say that we have some quantity of 50 milligrams of some substance and we're decreasing exponentially. Then we want to know how long does it take for that 50 to become 25, and that time again is on the horizontal axis. So this amount of time, whatever that might be, when you read off of that horizontal axis, is the half-life of that model. Example 1, an initial amount of radioactive substance is given along with the information about remaining after a given time t in appropriate units. For an equation of the form y equals y sub o e to the kt, or the PERT model, that models the situation, give the exact value of k in terms of natural logarithms and an approximation to 4 decimal places. So our problem set up here, again, we can use the P of t equals P sub o e to the RT formula and just fill in what we know. The y sub o, or the amount at the beginning, the P sub o is 30. E, we're trying to find the R, or the K. T is 6 hours, and the amount after a given time of 6 hours is 10. So we need to solve this for R. Simplifying this equation, I get 1/3 equals e to the 6r, and I can easily put this into logarithmic form. It's a natural log, of course, base e of 1/3 equals 6r. So I'm going to divide by 6. So my rate is 1/6 of the natural log of 1/3. Or I can also get an approximation, 1/6 times the natural log of 1/3. Close your argument, and I get an R of about negative 0.1831. That is your relative rate of decay. This is a decay model. Notice that our R ends up being negative. For this situation, we have Y sub O of 20, and the half-life is 200 days. So let's set up what we know. We know that the initial amount is 20, filling in, again, this formula. E to the, we're not sure what the relative rate of decay is. The half-life, though, is 200 days. So if I have 200 days, then this initial amount will become half of what it was. So what is half of 20? It is 10. So we're going to try and solve this for R. Again, we can go ahead and simplify that formula. 1/2 equals e to the 200r. Then we change to the exponential, change the exponential form to log form, and divide by 200 so that we have R solved for. R is equal to 1/200th of the natural log of 1/2. And again, we can put this into the calculator. 1/200 times the natural log of 1/2, and I get a relative rate of decay of negative 0.0035. Again, notice the rate ends up being negative, as it should. If you start out with 20 and after a few days then you have something less than that 20, that rate should be negative. It should be a rate of decay rather than a growth rate. A sample of 500 grams of plutonium-241 decays according to the function A of t equals A sub O e to the negative 0.053 t, where t is the time in years. Find the amount of plutonium-241 remaining after 4 years, 8 years, 20 years, and then we want to find the half-life. So we have a sample of 500 grams of plutonium to start with. That is our A sub O or our P sub O. So 500 e to the negative 0.053. If we're trying to find the amount remaining after 4 years, we'll put 4 there. And that is going to be our amount at 4 years. So we simply put this into the calculator. 500 times e to the negative 0.053 times 4. And we get amount at 4 years is about 404.5, and the unit was grams. Now that's part A. If I wanted to do part B, for 8 years, we can simply go up to this formula in our calculator and change that 4 to an 8. So the amount at 8 years is about 327.2 grams. And if we want to see how much is left at 20 years, we can do the same thing. Go back into the calculator, copy that formula, replace the 8 with a 20, and we get about 173.2. Part D, they want us to find the half-life of this this plutonium-241. Half-life would mean that this 500 grams goes down to 250 grams, and we want to know the time that it becomes 250 grams. That's going to be somewhere between 8 and 20 years, because 250 grams lies between the answers that we got for parts B and C. So rather than pecking around to try and guess what that time is, we can solve for it directly. If we're starting out with 500 grams of plutonium-241, and we have this relative rate of decay, and we want to know that the time, we can solve for the time that that 500 becomes 250. Now we can solve for t. So this will be 1/2 once you divide both sides by 500. And we have an exponential equation we can change to log form. So that's the natural log of 1/2 equals negative 0.053 t. And we'll divide both sides by negative 0.053. And t will be about natural log of 0.5 divided by negative 0.053, and that'll be about 13 years. About 13 years. And you can even check that in your calculator if you like. 500 times e to the 13 times negative 0.053, and we get about 250 grams. Here we want to find the half-life of tritium, a radioactive isotope of hydrogen, which decays according to the function a of t equals a sub o e to the negative 0.056 t, where t is the time in years. So again, we are trying to find the amount of time. We're solving for t, where the initial amount becomes half of the initial amount. So this initial amount, we weren't given an actual number for it, but we know that the initial amount is a sub o, and the rest of the formula is there. And at what time does this initial amount become half of the initial amount? That's all it is. We don't need to know how much we started with. We just know that whatever we started with, we will have half of it at the time that the half-life is approached. So we have to divide both sides by a sub o, and I get 1/2 equals e to the negative 0.056 t. I'm going to change this to natural log form. So natural log of 1/2 is negative 0.056 t. I'm going to divide both sides by that relative rate of decay. And I have t is equal to the natural log of 1/2 divided by negative 0.056. And putting that into the calculator, you can get a close approximation here of 12.4 years. Make sure to put your label of the time unit on those. You could have a half-life that is literally seconds. You could have a half-life that is thousands of years. So it's very important that you give what the label is on that time unit. Example 4, if 1 gram of strontium-90 is present initially and 2 years later 0.95 grams remains, how much strontium-90 will be present after 5 years? So again, we have a exponential decay. So P of t equals P sub O e to the RT using that PERT formula, and fill in what you know. We have 1 gram of strontium-90 present initially, and at 2 years later, we have 2 years for the time, 0.95 grams remain. So how much strontium-90 will be present after 5 years? Well, we first have to come up with a model for it. Right now, what we need to do is solve for our rate. I'm going to go ahead and change this because we don't have to have the 1 there. I can go ahead and change this to natural log form. Natural log of 0.95 equals 2r. I'm going to divide by 2 both sides. So r is about natural log 0.95 divided by 2. When you're reporting these relative rate of decay or growth, whatever the case may be, make sure that you show at least 6 decimal places. Since this is in an exponent position, it does have a lot of sway when it comes to round off error, especially when you're extrapolating any of this data further out. So you want to make sure that you're using enough decimal places here. So our model ends up as P of t equals 1 e to the negative 0.025647. Some of my writing is going away as I'm writing it. Sorry. Fix that. And the t is up there. So this is a model that you could figure out what your amount is at any time t, but we want to do the 5-year amount. So the amount present at 5 years is equal to 1 e to the negative 0.025647 times 5. And we simply put that into the calculator. So we're going to do e to the, instead of using that rounded value, you go ahead and use the amount that's in your calculator. Not only is it more convenient, but it's going to be more accurate the further out we go from the initial time. So we get about 0.88 grams. So that's the amount of strontium-90 present after 5 years. Here we have a sample from a refuse deposit that shows 40% of its carbon-14 has decayed when compared to that of a contemporary sample. So we need to know how old was the sample. This is not unlike something that you would be expected to do if you were a scientist trying to date objects, carbon-14 dating. So the decay rate of carbon-14 is known. What thing can we check to see what the carbon-14 decay rate is? Well, we could look it up in our book, or you could even go to a site like Google and say carbon 14 half-life decay rate. There we go. Carbon 14 decay rate. So the decay rate is, well, we know that it's half-life is 5,730 years, give or take 40 years. So 5,730. So 5,730 years is the half-life. And so we're going to have to use that to figure out what the decay rate is then. So if we have this, say we have some kind of a sample of 20, it doesn't matter what we put in there, 20 grams, then we have e to the r, whatever that rate is going to be, times the time, 5730. And that initial amount of 20 will end up being 10. Or if you had put 100 here, this would be 50. It really doesn't matter what you put here, just make sure that this is half of it. And it doesn't matter because once you divide by that coefficient of your exponential expression, then you're going to get 1/2 on the left side, e to the 5730r. And so we have natural log of 1/2 is 5,730 r, and r is going to be the natural log of 1/2 divided by 5,730. You're probably seeing a pattern here with half-life and natural log, and there is an extra formula that you can use to get straight to the decay rate given a half-life, and that is the decay rate is going to be the natural log of 1/2 divided by the half-life. So your relative rate of decay is about, this is a negative 0.12096.8, we'll say, but this is to the left 4 places. So starting here, 1, 2, 3, 4. So we have a decay rate of negative 0.000120968. Give it enough decimal places to avoid any round off error. So we have to figure out how old this sample was. So the sample from the refuse deposit shows that 40% of the carbon-14 has decayed. So what is the amount that was present initially? Well, it was 100%, or as a decimal, 1. E to the, we have the rate that we found, negative 0.00012. I'll go ahead and record it as that. And we're trying to figure out how old this sample is and what is the amount left at this time. So at whatever time this is, what is the amount that's left? We know from the problem that 40% of the carbon-14 has decayed, so that means that 60% is left, or 0.6 as a decimal. So we're going to change this to natural log form. Natural log of 0.6 equals negative 0.00012t. T is natural log of 0.6 divided by negative 0.00012. And of course, you're going to use the numbers that are in your calculator already. The natural log 0.6 divided by that relative rate of decay that's in your calculator, and we get 4,223, and that's in years. So it's 4,223 years old, this sample. Newton's law of cooling is an excellent use of the exponential decay model. It says that the rate at which a body cools is proportional to the difference in temperature between the body and the environment around it. This doesn't have to be like a person's body or an animal's body. It could be a cup of coffee. Okay, so it doesn't matter, some kind of mass that cools. The formula says that if D sub O is the initial temperature difference between an object and its surroundings, and if its surroundings have temperature T sub S, then the temperature of the object at time t is modeled by this function. T of t equals T sub S plus D sub O e to the negative kt. And K is that positive constant of cooling that depends on the type of object. Once you put that positive constant of cooling in there, the negative in front of it makes it a negative rate of decay, and then your temperature will fall as shown in the model. For example 6, we have a piece of metal that's heated to 300 degrees Celsius and placed in a cooling liquid at 50 degrees Celsius. After 4 minutes, the metal has cooled to 175 degrees Celsius. We need to find its temperature to the nearest hundredth after half an hour. So we've got a lot of work here. Let's go ahead and start this. I have the temperature of the surroundings is the cooling liquid of 50 degrees. And the initial temperature difference, so at the start of the experiment, we have this 300 degree piece of metal, and we have this 50 degree cooling liquid. The temperature difference between those is 250 degrees. So we're putting 250 as our D sub O. E to the negative K. We don't know what K is, so guess what? We're going to have to solve for it as the first thing that we do. We do have this data to put in. After 4 minutes, the metal has cooled to 175 degrees Celsius. So at a T of 4, the T of T is 175. Now we can solve this for K. The first thing that we need to do, though, is get this e to the negative 4k by itself. So we're going to subtract 150 from both sides. That gives me 125 equals 250 e to the negative 4k. I'm going to divide both sides by 250, so I happen to get 1/2 equals e to the negative 4k. And then I'm going to change this to natural log form. Natural log of 1/2 is equal to negative 4k. So I know that k is equal to natural log of 1/2 divided by negative 4, which means natural log of 1/2 in our calculator. Natural log of 1/2 divided by a negative 4, and k is 0.173287. All right, so we need to find, using that new information that we have, the constant of cooling, the temperature of the this object, this piece of metal, to the nearest hundredth after half an hour. Okay, so half an hour, you cannot use 1/2 because this is done in minutes over here. So we need to make sure that we are using the same time denomination. So 4 minutes, a half an hour is going to be 30 minutes. We have the temperature at time 30 minutes is going to be equal to 50 plus 250 e to the negative 0.173287 times 30. So we have 50 plus 250 times e to the negative, go up and borrow that constant of cooling that we just found and multiply it by 30 up there in the exponent. And we get the temperature at 30 minutes is about 51.38 degrees. So it is cooled almost to the same temperature as that cooling liquid. Here we have a Midwestern city that finds that its population is declining according to this function, where t is measured, it's time measured in years, and p sub o is the population at time t equals 0. Assume that p sub o is equal to 1 million. So they want us to find the population at t equals 0 and t equals 1. Let's take this model that they have and just flesh it out a little bit more. P of t equals, they tell you that p sub o is 1 million. E to the negative 0.04 t. So the population at time 0, we don't even need to put that into the calculator. We know that it's 1 million. So P of 0 is 1 million. If you want, you can put 0 in for t, but that's going to make this a 0 times the negative 0.04 is 0. E to the 0 is 1 times 1 million is 1 million. It's a good demonstration to see why this number here is your initial amount, the amount or the population at time 0. But you don't need to put that in there. Population at t equals 1. So P of 1 is equal to, we'll just put this into the calculator, 1 million times e to the negative 0.04 times 1. We're letting time be 1. So we get a 960,789. And round that to the nearest whole because we're talking about population. So you don't want 4/10 of a person there. All right, how long to the nearest tenth of a year will it take for the population to decline to 750,000? So we're going to take this formula here and let P of t be 750,000. And the rest of it is the same. And we're solving for t. We want to know what time goes with this P of t. So you could take your 750,000 and divide it by 1 million. And if you want to do that in your calculator, it turns out very nice. And we get 0.75. So really knocks the numbers down low for you. E to the negative 0.04 t changed to natural log form. So natural log of 0.75 is equal to negative 0.04 t. So we'll continue this over here, and t is going to be equal to the natural log of 0.75 divided by negative 0.04, and put that into your calculator. Natural log of 0.75 divided by negative 0.04, and 7 nearest tenth of a year, so 7.2 years. So after 7.2 years, then our population of 1 million has declined to 750,000. How long to the nearest tenth of a year will it take for the population to decline to half of the initial number? So we can speed this up if you like. This 1 million would become the 750,000 was 75% of the initial. If we wanted to be half, then this would just become a 0.5. So in reality, t is going to be equal to the natural log of 0.5 divided by the negative 0.04, and we can just go up and borrow that formula, modify that so that it's a 0.5 instead of a 0.75. Let's try that again. Delete that 7 and I get about 17.3 years. So in 17.3 years, our population will be half of what it was initially. How long will it take an investment to triple if interest is compounded continuously at 4.3%? So we've done problems similar to this before. Again, just using the PERT formula, P of t equals P sub O e to the RT. It doesn't matter what your initial investment is, e to the 0.043. We just know that we're trying to find the time that it takes the P sub O to become 3 times P sub O. When I divide both sides by P sub O, then I get 3. And I'm going to change to natural log form. So natural log of 3 is 0.043t. T is going to be the natural log of 3 divided by 0.043, and put that into the calculator. Natural log of 3 divided by 0.043, and that gives me about 25.5 years. Remember, your time with the interest formula is always in years. So 25.5 years it's going to take for that initial investment to triple. All right, the number of views of a YouTube video increases after the number of hours posted as shown in the table. Use the model y equals y sub o e to the kt, or you could just use the PERT formula, they're the same thing, to find an exponential function that gives projected number of views y after number of hours x. Let 20 correspond to x equals 0, 25 correspond to x equals 5, and so on. And use the first and last data values given in the table. So in our table, we are going to use for x a 0 for that first data point, and for the last one, since they're having us use the first and last data values, this is going to be an x of 15. So we can use the formula P of t equals P sub O e to the RT, and your initial, the number of views at hour 0 is 100, e to the r, and we need another time and a number of views at that time. So we can use a time of 15 hours, and the number of views at that time is going to be 10,248. We divide both sides by 100, so that's going to give me 102.48 equals e to the 15r, and I take the natural log form of this, and that's going to be the natural log of 102.48 equals 15r, and r then is going to be the natural log of 102.48 divided by 15. So r is approximately Put this into the calculator. Natural log 102.48 divided by 15, and I get a 0.308645. All right, so we have an exponential function we have to come up with for part A. We have the rate to do that now. So we'll say that the P of t is equal to 100 e to the 0.308645 t. For part B, we are to estimate the number of views after 50 hours. So if we have been letting 20 be 0, 25 would be 5, 30 would be 10, 35 would be 15. 50 hours is going to be an X value of 30. It's 30 hours after 20 hours of initial time where we start recording the number of views. So we're going to use the same formula that we had before, the P of, but we're going to use 30 equals 100 e to the 0.308645 times 30, and putting that into the calculator, I have 100 times e to the, we can go ahead and borrow that number that we just found, the 0.30846 times 30, and we get quite a lot. So 1,050,215 views after 50 hours. And that seems kind of incredible, but if you use this formula and put the other numbers in from your table, you'll get something close to what's in the table. Put 15 in there, and you will get your 10,248. If you put your 10 in, you'll get close. Put your 10 in there, and 2189. The reason this is spot on is because the model was made from the first and the last data points. But that's how a lot of the problems are modeled exponentially. And that should do you for your 4.6. So go ahead and try your homework and let me know if you have any questions.